Neurips 2024, part 7. This paper I'm discussing today is about smelling. So the authors, the links in the show notes, the authors are trying to align chemical structures with olfactory perception. In other words, you give people something to smell, and they classify it as this smells like jasmine or this smells like orange. And then you find the relationship between that smell and the chemical structure. So that's the goal here. Just as a preamble, we're not yet at the point where we can smell airborne chemical structures. So this is still text-based. And I think that's going to be part of the conclusion. Further work will have to be done in order to really get a multimodality where an agent, an embodied agent, can actually smell. You're going to have to identify airborne chemical structure and then perceive them. But we're not there yet. This study doesn't do that. What this study does is it aligns chemical structures, or written down formulas. There are certain models to do that, and it's all described in the paper. But think about it this way. There is actually a transformer model which was designed particularly for chemical structures. There are data sets for chemical structures. You have to think about how do you vectorize chemical structures. This is pretty deep work, okay? So it's not that simple, and it might sound very simple on the surface. Can AI models smell? But when you fundamentally start working on this, it's pretty involved, right? You have to take, let's say, the smell of jasmine. You have to first identify the chemical structure that relates to jasmine, then represent that chemical structure in machine understandable language, and then have an algorithm that trains based on this type of representation. And hopefully, if you have a transformer-based model, you have enough generalization that you can do one-shot prediction going forward. The authors are showing that that's possible. They're also showing lots of limitations, of course. For example, just one example, it's relatively strong, like it's not easy, but you can actually do pretty good binary prediction. So you can say, this is jasmine and it's not orange. You can say this is vanilla, but it's not strawberry. So that kind of thing works pretty well. Where you're not doing that well is, like, this is more intense strawberry than this, or this is more dark chocolate than brown chocolate. Like this continuous perception is not fully there yet. So that's already the limitation. But I think this is incredibly important work for really 3 reasons. One is it's part of the foundation model for embodied decision-making agents. So you want to add multimodality to those foundation models, and olfactory perception is certainly part of that. That's number one. Number two is the question of how to do this. What these authors are suggesting is that we take chemical structures and we align them with human perception. So we really ask a fundamental question, which is the way we humans perceive odorants. Is there a structure to that, and can we implement that structure in AI? And the answer is yes. There's actually a lot of overlap. And then the third, which these people are not really talking about yet, is like airborne or olfactory perception. So this would be the holy grail. Your Tesla drives and it smells gas, and it stays away from wherever it smells gas because it knows that that's dangerous. Or actually a much more useful thing would be your home system, which is hopefully much better than Nest, which is a disaster, just as a tangent from a customer perspective. But you really have an intelligent home system that smells gas, carbon monoxide and things like that, and realizes, hey, there's something wrong here. Now, we already have systems like that, of course, carbon monoxide, alarms and things like that. So there's some of that already happening. But what we're dealing with here is, of course, not an ASIC. This is not an application-specific integrated circuit that deals just with gas or carbon monoxide. This is a generally trained transformer, which is trained in a way to represent chemical structures. Okay, so let's dissect this first. So we have a transformer, and there's actually work in the paper discussing what they're using. The actual model is called MOL former. That's a specific transformer model for chemical structures. What I found interesting is when you look at the actual data representation of the chemical structure. So, for example, carbon dioxide has a certain chemical form, right? And we learned that in high school. And that needs to be represented in machine understandable language so it can be vectorized. So that in itself, I think, is a math problem. People have thought about this. There are solutions to it. I think could be more work done on this front. But the fundamental idea here is that we translate chemical structures into language the same way we translate Shakespeare into language. We tokenize the whole thing. We train it on a transformer and attention-based network, and then we have generalization, self-supervised learning, because one of the problems with chemical perception is the problem of labeling, right? I mean, you can use labeling to some extent, but this is, of course, much more powerful. Like everything else in the transformer space, we have lots of data and very general models, and we can actually learn a lot more chemical structures. In particular, when we start going beyond the binary classification of, again, this is vanilla versus this is strawberry, towards more intense, less intense, you can see that the action space, of course, infinitely grows, and we want to have general models. So that's I think one of the most interesting things that this paper comes up with. I think what's also interesting about this paper is that it actually works, right? So the representation of chemical structures that correspond to certain, let's say, olfactory perception. So the chemical structure that represents jasmine, or the chemical structure that represents chocolate, actually there is an alignment, right? So if we put that chemical structure and give it to the model, it predicts this is chocolate, and then a human would take the same chemical structure and predict that this is chocolate. Actually, to my knowledge, this has been done by companies like Givaudan, for example, in Switzerland. That's what they do. These artificial sweetener type companies, or artificial taste companies, like when you have zero Coke, right? Zero everything. How does this thing even taste like Coke, and why does it taste sweet? It's because companies like Givaudan, there's another one in the US, have figured out how to trick your brain with a chemical structure that represents the taste of sugar and the taste of Coca-Cola. So that's already, I think that this type of work has already been done for decades, right, in the chemical industry. What we're doing here is, of course, we're now building AI agents that hopefully one day can smell airborne jasmine or strawberry, and predict that. So the use cases here could be many. Like I said, for example, you could smell carbon monoxide or gas, but you could also smell when apples are ripe. You could smell when something is just about to turn sour. Let's say your refrigerator could smell when your milk is about to turn sour. Oh, smell is pretty strong. Smell as a sensory technology is pretty strong. Look at your dogs. My cat is incredibly good at smelling stuff. Animals have very good senses of smell, most of them. And I think our AI agents could also be incredibly powerful with smell. Even your Tesla car, empowered with smell, could have additional use cases. Even just a simple one, which is your Cybercab of the future could smell when it needs to be cleaned, or it could smell when somebody puked, things like that. So I think olfactory sensory inputs are incredibly important for AI agents. And I think I want to just sort of lean back for a second and just discuss this a little bit more philosophically. You might think, when I first saw this paper, I was like, yeah, I mean, come on, who cares? Like, we have more important fish to fry than how can transformers smell? Like, but then once you start thinking about the problem, first, it's a very interesting math and engineering problem. Like I said, the math question is, how do we actually represent chemical formulas in vector form? The engineering side of things, how do we actually train this? And then the use cases, like I just said, I mean, think about what Tesla could use with olfactory sensory inputs. in the Cybercab world, right? I mean, amazing. Like you could have, the cab could sense when it needs to be cleaned. Of course, you could use vision too, but sense, smell is really more powerful. It's the same with why do we use dogs to sense for drugs? Another use case right there, right? You could have drug smuggling could be much more difficult because now we can go, Hilbert space in terms of maybe not Hilbert space fully, but definitely many more dimensions in terms of smell and intensity. The authors say that they haven't really solved for intensity or anything like that, but I think I guess my conclusion here is that olfactory sensory input, like vision, like video, like sound, all of these things are terribly important, and we shouldn't discount them. Just because vision works really well right now, I think it's worth working on the other sensory inputs. Nature has given us a couple of sensory inputs: touch, smell, sound, vision. I think we should be exploring all of them. And like nature, like evolution, I think we shouldn't just go with one. Like look at humans. Like we have good vision, we have a very strong brain to interpret actually vision. That's why our vision is not really that good, but the interpretation of what we see is much better than any other animals. And but then our dogs have much better smell, our cats have much better smell. There's animals that have really good touch, and there's animals that have good ears and things like that, owls, I believe. So why don't we build this super amazing embodied agent that can smell and hear and see, and that's where this is going. I think that's in that context I see this paper as really powerful. Thank you.